Thank you for your attention. I'm Leigh Orf. I'm a scientist at the University of Wisconsin. I do work on numerical simulation of thunderstorms, and I'm primarily interested in the most devastating thunderstorms, namely supercells that produce the most devastating tornadoes. So my research goals as a scientist, we're trying to understand how tornadoes form in supercell thunderstorms. We really don't have a very good idea of all the mechanisms that go into tornado formation, specifically genesis, the formation of tornadoes. We want to also know, once a tornado has formed, what are the processes going on within the storm that maintain it throughout its life. And also, a really important question is why some supercell thunderstorms produce these long track EF5 type top end tornadoes while others do not. So essentially, the process is to simulate the storms on supercomputers. We're using blue waters, visualize and animate high-quality representations of the model output. I'll show you some of that towards the end of the talk. And then do quantitative analysis, parcel analysis, tell a story about what's physically going on inside the storm, and then, of course, compare to observations, which is always something you need to do in meteorology. We're using CM1, a cloud model developed at NCAR. It contains about 10,000 lines of Fortran. It's pretty good. The solver's pretty fast. It utilizes non-blocking communication when possible. The solver scales well to hundreds of thousands of MPI ranks. I just yesterday was running a job that was over 300,000 cores on blue waters, about 40% of the entire machine, one job, one MPI job. We also use a little OpenMP as well. We're splitting the job up 15 ranks, or 16 MPI ranks, which is the number of cores on blue waters. And that works pretty well for us. Now, the big problem we had was I/O, which probably shouldn't surprise you. We're studying tornadoes, and tornadoes move really fast, so we need to save data very frequently. And much of the work I've done in the past decade has simply been dealing with I/O and data and managing data. So the scope of the problem, there's an earlier slide about NCAR and how if you double the resolution, it takes 10 times more resources. That's, that's basically the problem, 8 to 16 times more computations because you have to reduce the time step as well. In the field of meteorology, if you read the journals, a typical very high resolution simulation is about 100-meter grid spacing. We're running at 15-meter grid spacing. That's the highest resolution simulation I've done thus far, which is 3 orders of magnitude more computation per simulation. Okay, so this is really out there research. We're really hitting this stuff at the highest resolution we can do. We can probably squeeze a little more resolution out of blue waters and get up to more of the machine, but this is a pretty big problem. 18.4 billion grid cubes are simulated. So the biggest bottleneck was I/O. We need to save data frequently. We save about 15 variables. I need to save data every one model second. So if you just do a quick back of the envelope calculation, 15 variables, 32-bit floating point data, it's about 2 gigabytes of lossless floating point data per time step. You save 7,200 time steps, about 2 hours of cloud time. That's 16 petabytes of data, and that's just not going to happen. So what do? I accidentally created a file system. I say that because it was funny. I was talking to a computer science guy at the last Blue Water seminar, and I was explaining what I did, and he said, "Oh, you created a file system." And I said, "Oh, cool. I guess I'll name it." So LOFS, LOFS, Leigh Orf FS, lack of file system, all sorts of ways you can describe this. Basically, I'm shoving all my data into HDF files, multiple layers of times per file, 1 file per node, not per core. So each file is about 1 to 5 gigabytes, nice fat files being sent out to the Lustre file system. I should probably write a paper about this at some point, but essentially, I'm using HDF, the core driver, which allows you to buffer files to memory. So I also use rank reordering in order to get the model mapped to the hardware in a way such that if I'm collecting data to one of the cores on the node, it's not all scrambled up. So rank reordering allows us to map the 2D decomposition to the hardware in a logical way so that all communication when doing I/O is intra-node, and then saving it, growing it in the file, growing it in memory, which is much, much faster than sending it to disk. And once you run out of memory, whoosh, send all that stuff to the Lustre file system. And supercomputers tend to do pretty well with that kind of approach. So not only that, that haven't addressed the amount of data problem. Further reductions can be found by only saving part of the simulation. So I'm looking at tornadoes, but I'm simulating a thunderstorm in the surrounding environment. We can maybe just look at what's going on near the updraft of the thunderstorm. That might save you about 5 times. But what really sort of gave us a big advantage was using lossy floating point compression. This is something brand new to me. We're utilizing ZFP. We get about a 20 times reduction. Now, you have to be able to live with lossy data at this point, but it's a very good algorithm. So now instead of 16 petabytes, we've got 160 terabytes of data, which is much more manageable. Okay, so once you got the data on disk, you have to do something with it, and I wrote an API and a bunch of software that sort of treats this file system as a file. So you can essentially go out and request a certain subset of the full model domain. The code goes out and goes to the right files, pulls the data out, stuffs it into a 3D buffer, and then you can do things like create a netcdf file, use it as a Visit plugin, Visit software developed at Lawrence Livermore that I use quite a bit, or convert to a netcdf file and share it with your collaborators. So for the rest of the talk, I'm going to sort of show you some of what this all manifests. This is the full model domain for a 30-meter simulation showing the cloud. It's 120 by 120 by 20 kilometers. I like to show these images because they give you a sense of the scale of the problem. So here's this really big thunderstorm, and here's this, looking like a pretty small tornado, but all the action right here is what we're interested in. This was done using the Visit software. And here's some terms, tail cloud, tornado, rear flank of the storm, forward flank, mesocyclone. These are all standard things in severe storms meteorology. So here's a recent simulation I did. So this is at 30 meters again. Here's your cloud. You've seen the tornado form right here. This is rain. This is the cold pool of the storm. I've put some slices, 2-dimensional slices. This is the updraft at 1 kilometer, the reflectivity, what you'd see on radar. And I'm just zooming ahead here. But essentially, all you see here is a pretty amazing stuff. There's another vortex that kind of goes around the main tornado. We're seeing all these features that have been identified in the field showing up in the model now that we've reached sort of a resolution threshold. And it took a lot of work to get to this point. And being able to save data every 1 second was a challenge, but this is what I knew I had to do. So I did all this back-end stuff before we even did the simulation. Here's another animation of the vorticity field, or the field that sort of defines the spin. This would be like the core of the mesocyclone. This is that updraft. Again, what you'll see is eventually a tornado forms right sort of back over here. You're seeing over time, so as time goes on, the storm is sort of getting its stuff together. You start to see more organization right about here. So you've got this air that's generated in the cold pool of the storm that's being lifted into the updraft. We call this sort of rotating helical flow, the streamwise vorticity current. It seems to help make the updraft stronger, which helps to create the tornado. We haven't really put all the pieces together yet. At this stage in the game, I've just got the second year of my PRAC allocation on Blue Waters, and I'm just chomping at the bit to create data. We can analyze it later, but creating the data is very important. This is using Visit at NCAR, dropping trajectories in, showing the streamwise vorticity current in action. These are essentially massless particles being sucked into the updraft of the storm. It makes this turning and rises into the storm. It doesn't actually interact with the tornado directly, but seems to help the updraft support the tornado. This is a 20-meter simulation. Using Visit again, showing this multiple vortex tornado. Now we can really see the individual vortices inside the cloud. I will zoom in a second and also compare to some observations, but you can see if you look closely, the rain, this is rain in the rear flank of the storm and all these vortices. All I'm showing is the cloud and rain field, that's it. Slowing it down a bit, I'm going to compare this to an observation took at the side of I-39 by some guy who got stuck by this EF4 tornado that occurred in 2015. So he really wasn't supposed to be there, but he filmed it and he lived. So I take this video, but I use this to compare. I mean, we have to compare to observations, and essentially, if you look carefully at his footage, you'll see that there's individual vortices in here. You see the same thing in our model data, and this gives us a lot of confidence that we're on the right path here. This kind of high-resolution tornado simulation where you simulate the entire storm like this is kind of new territory. And this is a 15-meter simulation. This was completed last month. Now you're starting to see the clouds are more cellular. They look more bubbly like you see in nature. The tornado in this case just churns along. I've got hours of quote-unquote footage of all this stuff, just trying to basically make movies to sort of get a feel for what's going on before we take this data into the quantitative realm and start doing some serious analysis. But essentially, I would say that Blue Waters has been an incredible resource to me. I'm very excited to be doing this kind of research. I think it's going to be, we're going to have decades of data to paw over from this. Here's the vorticity field again showing the generation of a tornado. I really have a lot of fun with volume rendering, as you can see. I've tried a whole lot of different tricks to do the volume rendering on blue waters. I can basically make, say, 5 minutes of video in, say 6 actual wall clock hours if I can spread the jobs out enough. It's a lot of fun. But anyway, thanks for the invite, and if you want to see some more cool movies and stuff, I have it on my website, and I'll be happy to take any questions.
Fantastic work. So I'm assuming your end goal in all of this is to try to figure out how to potentially design something that will help dissipate tornadoes, or what would you like to see your research?
I would say the end goal is to produce better forecasts. I'm not thinking weather modification is going to be a main thing. It could be, though. I mean, as we start to really look deeply into these simulations, we might be able to find a way to do some sort of weather modification approach. But the end goal for me is, once we understand these storms better, we'll be able to look at radar while the storms are forming, key in on features that we now understand are correlated with tornado formation, and issue better warnings, more targeted warnings, and more specific warnings, like this is going to be an EF5 strength tornado. This is going to be a short-lived tornado. Those are the kind of things we'd like to be able to do.
So in order to get there, what kind of computation would you need? If you were able to say, here's the real-time radar, I want to predict ahead so that I know a half an hour, what's my probability? What kind of systems would you need?
Unfortunately, the computing system's only half the problem. Let me just say before I sort of address that, or try to, it's observational data that's the most important. It's garbage in, garbage out. It's an initial value, boundary value problem. And if you start with bad initial conditions, you're going to have a bad solution. But assuming we could get all the data in the world that and get really accurate data surrounding the area where the storm's going to form and predict it, we're talking exascale, I mean, without a doubt. And not only, you're not going to be able to just do one of these simulations, you need to do what's called an ensemble of simulations, where you slightly modify the initial conditions to get a spread, like we're seeing with Hurricane Irma, right? When you see Hurricane Irma pass now, you're seeing like 12, 16 plots going up the Florida Peninsula. With this, we need to do the same thing with tornado forecasts, so we have a spread. And that gives us a probabilistic spread, and then we can actually issue a probabilistic warning or a watch. It's going to be the computing is only half the problem. I think the computing is the easier part of this problem. It's the data, getting atmospheric data to feed the model is going to be the bigger challenge.